In 8.8, we're talking about improper integrals. Now, what makes an integral an improper integral is one of two things. Either you end up going to infinity, or you try to integrate across a vertical asymptote, or any sort of discontinuity. So when we do the improper integral, there's two ways you can do it. You can do it very direct, where the direct version of this would be we're going to take this integral not from 0 to infinity, but from, sorry, not 0, but 1 to b of 1 over x squared dx. And after we do that, we're going to take the limit as b approaches infinity. Because you can't really plug in infinity. But in the end, you kind of can anyway. So let's see what happens here. So the antiderivative of 1 over x, this is really x to the negative 2. So we add 1 to it, x to the negative 1 divided by negative 1. So negative x to the negative 1. Valuing this from 1 to b. It's giving us negative b to the negative 1 minus 1 to the negative 1. Okay, so we end up with negative 1 over b minus 1. But remember, we have to do the limit as b goes to infinity. So we end up with limit of negative 1 over b minus 1. And we're taking b to go to infinity. So as b goes to infinity, this first part drops out, and we're just left with our negative 1. So the non-formal version is, well, what happens to this if I was to just put in infinity here? Now, this is not very good mathematics, but it still gets at the right answer in the end. So 1 over infinity, taking 1 and cutting it into an infinite number of pieces, that's really 0. Minus 1 gives us negative 1. All right, let's see another one. Now, you might assume that since we saw what happened with the last one, that this would do the exact same thing. But the antiderivative of 1 over x is ln of x. And if we're going to plug in infinity and 1, ln of infinity, which is not a very good thing to do, you can't really plug in infinity. You have to look at the limit as it goes to infinity minus ln of 1. But natural log of something as it goes to infinity is infinity minus 0. So this ends up being infinity, which is the definition of a divergent integral. So kind of pass up the definition of convergent or divergent. And convergent is if it converges to an actual number. And divergent is if it doesn't get us an actual number. Now, some of them are kind of obvious. So like 3 here, well, we get e to the x times x. That's going to be just huge. If we're taking this to infinity, well, it's really going to be very huge. Now, the question is, do we end up getting it where it cancels out? Where on the right you get infinity, and on the left you get negative infinity. And then the question is it symmetric? Does just the area of the curve drop away? So what we're going to do is, sometimes you can break this into 2, or you split it down the middle at 0. We'll try to do it the way it is. So I've got 2 parts, so I got integration by parts. So we're going to let u be x, and the v be e to the x. So du equals 1 v e to the x. So we're going to do our whole integration by parts deal. So u v x e to the x minus the integral of v du. So e to the x. So we get x e to the x minus e to the x. And we got to plug this in from negative infinity to infinity. Well, when I plug in infinity, you could talk about you've got infinity minus infinity, but you get a much bigger infinity minus a not much smaller infinity, but we're going to end up getting infinity in the end. Minus, now if I plug in negative infinity, I get negative infinity over e to the infinity plus e to the infinity. So I don't have an extra negative, do I? Well, what happens is this is a smaller infinity on top because it's just x as we're plugging in infinity divided by a huge infinity on the bottom. This part ends up dropping out to 0. And then we end up adding another e to the infinity in here. So this works out to being infinity. And the reason for that is if you look at this graph, e to the x on the right side explodes huge. But on the left side, if you go to negative numbers, e to the negative x, that drops out really small. On the left side, it really approaches 0 really fast. So on the right side, you get all this huge area under the curve. On the left side, you end up getting it closer and closer to 0. So that's why that one doesn't end up dropping out. And actually, my graph's a little bit poor because if it has to be negative on the left side, but it ends up approaching 0 really close. It has to be negative because you have a negative times a really small number as you go to negative infinity. So you can look at it graphically and see why this should be infinity and not 0.